Okay, can you see my presentation?
Yes.
Yes.
Oh.
Oh, it looks very nice.
Thanks, Rita.
Okay, good morning and good afternoon, everyone, depending on the place where you are. Especially, I warmly welcome our next invited speaker, Dr. Riana Roux, from lovely and beautiful city Stellenbosch in the south of South Africa, close to the Cape Town and Cape of the Good Hope. Riana is a scientist and a lecturer at the Division of Applied Mathematics at the Stellenbosch University. Her research area is graph theory with specific focus on domination in graphs. I had the pleasure to work with her in the topic of domination and criticality in graphs. Riana visited Poland many times. She was even 2 times at my Gdańsk University of Technology. She participated in the conference that we organized, and she was also here with Erasmus program. Today, Riana is going to talk about some variant of well-known problem. It's a game of cops and robbers. Here in this case, the robber is invisible and the cop just have to locate the robber. So this game is called a localization game on graphs. So I invite all of you to listen to the talk of Riana Roux about localization game on graphs.
There you go. I nearly couldn't find my unmute button. So,
Okay,
good morning.
Sharing me. Okay, it's your turn now.
Thanks, Magda. And good morning / good afternoon to everyone that's listening. I must say, Rita, it's very nice to be here online, but I would really have loved it so much more to be in Mexico right now. But we all suffice with sitting in my office. So as Magda said, that today I'm going to talk to you about the localization game and graph. I'm going to start off with just an introduction to where the game comes from and how it works, and then move on to some general results. And after that, we're going to look at some special graph classes, and I'm going to conclude this presentation with some open questions. This is a relatively young game, the final game with K-Cops. So there's quite a few open questions. I'm just going to mention a few, but if you're interested in this type of games, this is actually quite a nice area to go into. So we're going to start with where it all comes from, and this is the classic game of cops and robbers. And in a game of cops and robbers, what they want to do is, you're playing this, it's a 2-player game, and the one player is a team of cops, let's say K-Cops, and the other player is just one single robber. And I find it very funny that in literature, the robber is a woman, so they always refer to the robber as she. And I can't get myself to do that. It always turns out to be a he when I talk about a robber. But anyway, this woman robber is trying to get away from the cops, and the aim of this game is to capture the robber. And with capture, I mean that the A cop must occupy the same vertex as the robber. So let's look at how this game will work. To initialize the game, the cop starts and he places, the K-Cops occupy K vertices on the graph. That would be these blue vertices. After that, the robber pick a vertex to be. Now, this game is played with perfect information, which means that both the robber and the cop knows where the other player is. And the robber is just trying to run away from the cops. This is a typical cops chase robber game, just on a graph. So after the initialization step, what happens is that the cop can now change position. So start to chase the robber. Importantly, this cop can only move to its neighbors or stay put where it is. So it can only move in the close neighborhood of the position he is currently at. So typically what we would suspect to happen if we're running after a robber rather, in a street, you can only go down the street. You can't jump suddenly to the next point. So only move to your neighborhood. If after this step, it happens that there's a cop on the same vertex as the robber, then the cop wins. Otherwise, the robber gets a chance to move, and the robber can then also move to some vertex in its close neighborhood. It can also stay put where it is, but it can move only in its close neighborhood. And then we start again. So you go on and on and on in a circle. And if it happens that after a finite number of times the cop occupies the same vertex as the robber, the cop wins. Otherwise, the robber wins. What we are interested in this game is the cop number of a graph, or one of the things that you can be interested in. There's many things, but we want to know what is the minimum number of cops that is needed to win, for the cop to win in this graph, which means that irrespective of what the robber does, how many cops do we need to win in a finite number of steps to occupy the same vertex as the robber? So that's the idea of the game of cops and robbers. I'm going to now work through an example so that we can see how this game works, just to get a feel of what we are doing in the cops and robbers game. So we're going to play it on a cycle, specifically on a cycle on 10 vertices. And we're going to show that the cop number of a cycle on 10 vertices is equal to 2. In general, this is also true. So this is just a small example of how it works on cycles. Now, in order to show that it is equal to 2, we have to have some argument that shows that a cop can never win with a single cop. So let's say we have one cop and we place it somewhere in the graph. It doesn't matter where we place it because this is vertex transitive. Now, this is our first initialization step for the cop. Now we want the robber to initialize his game or her game. See, I did it again. And the robber can choose any position. Obviously, the robber would not choose a vertex adjacent to the cop because then the cop will win in the next move because the cop moves first. But he can be anywhere else in the graph. And now, when we play the game, every time that the cop moves one forward, the robber just runs away. So it's like running in circles. The cop chases the robber in a circle, and the cop will never catch the robber. So therefore, one cop is not enough to win on a cycle on 10 vertices. It is, however, very easy to see that 2 cops will suffice. So if we probe if there's 2 cops on the graph, it can be anywhere. This is just the most balanced way. Then the robber can choose a side in which he wants to hide. So let's say the robber is located here on the right-hand side. Now the cops are just going to close in on the robber. So the strategy here to show that it is equal to 2 is just that the robbers close in on the cops close in on the robbers, that way around. The robber can move, but it doesn't really make a difference. And then in the third turn, the cop occupies the same vertex as the robber, and therefore the cop wins. So this shows that 2 cops would be enough to catch a robber on a cycle. And this is true in general for all cycles of order 4 and more. So this is the game of cops and robbers. Very classical game. So the game that we are going to talk about tonight is a generalization of this game. Actually, not just of this game. It's actually just the same kind of flavor. It is more of a generalization of the metric dimension. It's making the idea of the metric dimension a game, and we'll get to what the metric dimension is a little bit later. The aim of the new game is a little bit different to the one that we just seen in the cops and robbers. With cops and robbers, we want to catch the robber, meaning we want to occupy the same vertex as the robber. In the localization game, we just want to locate the robber. We just want to know where it is. In my mind's eye, I see this like an old school kind of cops and robbers versus a new school kind of cops and robbers. Old school, you actually run after the robber. You're in the streets and you know the robber turns this way and you run around. New school, catching thieves. You sit there in your office behind your computer and you ask for information. If you locate the robber, you send in the SWAT team. This is my idea of how I see these two, the difference between the location games. So in the localization game, this is one of the differences. So I'll hint on all the other differences while we're busy. When we initialize the game, it is the robber that chooses first. In the cops and robbers game, it was the cop that places the cops first and then the robber. But in the localization game, the robber is first on the graph. But a very important difference is that the cops has no idea where the robber is. If they did, the game was over because we just want to locate it. So the cops does not see the robber. It's invisible. So we are playing with imperfect information. So after the robber appears somewhere on the graph, we start our game and we enter the cycle. And in the first turn, the cop starts and so this is not K cops now, it's one cop doing K things. So he probes K vertices. And for this probe that he does, is he asks that vertex, how far is the robber from that point? And if you want to think of it, of why you want to use such information, it can be like a Wi-Fi tower, and that tower will give you the distance of a person with a device from prison that he couldn't take off his arm or his leg or something. And that Wi-Fi tower just tells you how far it is from the tower. So that is what this probe does. It tells you, okay, the robber is 5 meters from me, but I don't know in which direction. So the cop probes these K vertices. And then in the next step, he receives these distances. After he receives these distances, if he can locate the robber immediately, he wins. If he can't, the robber is allowed to move. And it can only move to its neighboring vertices because the robber doesn't have any superpowers. After the robber moves, we go back, and now the cop can again probe vertices. And here's another difference to the game of cops and robbers. Because the cop is not physically on the graph, he can probe any vertex. It doesn't have to be in the neighborhood of the previous probes because he's sitting somewhere else. He's just asking for information. So he can probe any K vertices, again receives the distances, and it proceeds in this way. I have to mention at this point that there is a restriction on the robber's movement because the robber can only move to its neighborhood. When the cop probes again, he knows where to search for the robber. He knows that the robber can't be somewhere here on the white vertices. It must be somewhere here in the pinkish kind of vertices. So you kind of get a restriction on your graph from in that specific turn where your robber can be, which makes it a little bit easier to find. You're not always searching on the whole graph. When the cop can't locate the robber in a finite number of steps, we say that the robber wins. And the parameter that we want to consider in this case is called the localization number of a graph. It's indicated with zeta. And that is the minimum number of probes that we need to win. So the minimum number of vertices I ask a distance from at every turn that will ensure that we win this game. And that is irrespective of the robber's strategy. So you have to consider all possible scenarios for the robber to ensure that the cop will win. To illustrate this game further, we are going to consider the same graph as with cop number to show that the localization number of a cycle is just 1. We don't need 2 cops to locate a robber. So let's consider probing one vertex on this graph. So the cop asks this vertex here at the top, what is the distance to the robber? Now we don't know where the robber is, so we have to look at all possible scenarios. So let's see what the distances are from this vertex. So in here, we indicate that these first 2 vertices are at distance 1 from the cop. Then we have 2 vertices at distance 2, 2 vertices at distance 3 and at 4, and then just 1 vertex at distance 5. So if the robber was located at this vertex at distance 5, or at the vertex where the cop probes, then we will immediately locate the robber, because there's just 1 vertex with that distance from the cop. At all the others, we have these safe sets. So it's a set of vertices where the distance to the cop is the same for all the vertices in that set. We call that a safe set. So we have 4 safe sets. A safe set at distance 1 from the cop, at distance 2, at distance 3, and distance 4. Now, if we consider these safe sets, you will notice that 2 of them is kind of similar. So this vertex, the vertices at distance 1 away, the 2 vertices in that safe set is at distance 2 from one another. That is the same for the vertices at distance 4. They're also at distance 2 from one another. And then the vertices at distance 2 and at distance 3, once again, have the same structure. They are at distance 4 from each other. So we just have to consider those 2 cases and see what happens if our robber is at one of those 2 safe sets. So firstly, let's consider the case where the cop receives the distance of 1 when he probes this vertex. Now this means that the robber will be at one of these 2 red vertices. So because the cop can't immediately locate the robber, it's at one of 2 positions, the robber gets an opportunity to move. So in the next turn, the robber can be anywhere in this gray band. We don't know where, but we know it can be anywhere in this gray band. So when the cop probes again, he doesn't have to worry about these white vertices. He only has to worry about the vertices in the gray band. So if the cop now probes the vertex in the end of this gray band, everything will be uniquely determined by its distance to this vertex. So then the robber can be immediately located. So that's for our first case. We have a strategy so that the cop can win. What about the second case? So that is the case where it receives a distance of 2 or of 3. It's the same scenario. So if it receives a distance of 2, the robber can be at one of these 2 red vertices. And after it has moved, it can be somewhere here in the gray areas. So if we now have to probe again, it would be easy for you to convince yourself that we can't immediately locate this robber. Because if I probe anywhere in this gray band, the other gray band will contain a safe pair. So for example, if I probe the vertex at the end of one of the gray bands, then the left-hand side will be uniquely determined. So if the robber was in the left-hand side, then we would know where the robber is and the game will end. If it is at this vertex, at distance 5 from the cop, we will win. But the robber can still be at one of these vertices at distance 4 from the cop. But if we look closely, we can see we know what to do with those kind of safe sets. It's a safe set where the vertices is at distance 2 from one another, which means that if we use our first strategy, that the cop can win in the next round. And therefore, 1 cop is enough to locate a single robber on a cycle on 10 vertices. And this is true for all cycles of order 7 and more. If it is of order 6 or less, then the cycles are too small and we're always back in a safe set if we just probe 1 vertex. Then we need at least 2. Okay, so this gives us an idea of how the game is played. So now we want to go on and see if we can find some general results on this game, some bounds and so forth. So I mentioned that this is kind of a sequential metric dimension game. So for those of you that knows what metric dimension is, I'm pretty sure that you've realized this already because we are looking at vertices that can be uniquely determined by their distance to some other vertices. So let's look at the metric dimension. So the metric dimension is the minimum of a graph, is the minimum cardinality of a resolving set. And a resolving set is a set of vertices such that all the other vertices in the graph can be uniquely determined by the distances to that vertex, which means if you find a distance vector for each vertex containing all the distances to the vertex in the set S, then every vertex has a unique distance vector. So let's look at a cycle again for an example. So we can show that the metric dimension of a cycle is equal to 2. Now, firstly, if you just ignore the orange writings for a little bit, you would be able to see that 1 would not be enough, because if I only have one vertex in my set, the green one, then there are vertices that is the same green distance from that green vertex. So it's not a resolving set. But now if I add the orange one, and I look at all these different pairs of distances, I can see that every single one of them are different. I have 1, 2, but there's not a single other one, which, I mean, there is one with a green one, but then the orange ones differ. So where the green ones are the same, the orange distances are different. So therefore, all the vertices in this graph will be uniquely determined by their distance to these two vertices. And therefore, we have the metric dimension as 2. So if we think about exactly the game of localization, of the localization game, then if I probe two vertices in a cycle, like in this figure, then I will immediately be able to locate the robber, because every single one of them have a unique distance. So that means that the metric dimension of a graph tells me how many cops or how many probes I need to do to find the robber immediately. So in one step. That's another way of seeing the metric dimension. But what this means is that the localization number of a graph will always be smaller or equal to the metric dimension of a graph. And trivially, it will be bigger or equal to 1. Now, we've seen with our first example on a cycle that the localization number of a cycle is equal to 1, so we can reach this lower bound. So now a question that we want to answer is, can we reach the upper bound? Can we find graphs where the localization number and the metric dimension of that graph are equal to one another? The answer is yes. It's an easy yes. I'll show you now. The second question we want to consider is, can those two differ substantially? So if we look at the localization number and the metric dimension, can we find graphs where the difference between those two parameters are quite large? That's the two things that we want to look at now. And to answer those two questions, we're going to consider two very nice graphs, the complete graph and the star. So for a complete graph, we're going to use the complete graph to show that the metric dimension of this graph and the localization number will be equal to one another. In fact, it's equal to 4. So for any complete graph, Kn, the metric dimension and the localization number will both be equal to 1 less than the number of vertices. And I quickly want to talk through this with you. So let's say for the metric dimension first, we choose just 3 of these 5 vertices in our resolving set. Let's do it with this bottom triangle to the right. If we now consider the vertices, the 2 vertices left at the top, you will see that the distance from all these 3 vertices at the bottom, everything is 1. So the distance vector that we get is 1, 1, 1 for the one and 1, 1, 1 for the other one. So they're the same, which means that a set of 3 vertices will never be a resolving set. So we will always need one more. So that sorts out the metric dimension. Now thinking about the localization number, let's say we again probe those 3 vertices at the bottom as our first probe. Then these 2 at the top would be a safe set. So the robber would be safe there and we won't immediately locate the robber. But in the next step, the robber can move anywhere on that graph again. So then we're back at step 1. We didn't learn anything, nothing became smaller, we can't solve anything. We're just back at square 1. So whenever we play with less than n-1 probes, we can't catch the robber. So we need exactly n-1 for both of these. For the star graph, we can show that the difference between the localization number and the metric dimension can be as large as you want. So let's look at that, do that a bit slower. So for a star, to find the metric dimension, let's say we certainly know that one vertex is not enough. So let's say we have 2 vertices in our set and we want to check whether it's a resolving set. So it's not going to make sense to pick the middle vertex as part of a resolving set because all the other vertices have exactly the same distance to the middle vertex. So we're going to start putting leaves in our set. If I have 2 leaves in my set, then there will be 3 vertices that have exactly the same distance to those 2 vertices. So it's not a resolving set. If I add more, I'll have the same problem because I have 2 vertices left. I need at least 4 of them in order to get all vertices different. Oh, my word just failed me. Different distance vectors. So in this case, you can see that every single one has a different distance vector, and therefore the metric dimension of a star is equal to 1 less than the number of leaves. So in general, if we have a star K1s, it is S-1. Now for the localization number, we can do a lot better. In fact, we can locate the robber by only using 1 cop. And how we do that is we probe 1 leaf, then the middle vertex is uniquely defined. So if the robber is at the middle vertex, I immediately catch the robber. So the robber can only be at the other leaves, safe at the other leaves. So in the next step, when the robber moves, the robber cannot move to the vertex that you just probed. So we lose 1 vertex in our star. So then for the next step, I'm just going to probe the next leaf. If the robber's there, I win. If it moves to the middle, I win. So then it's going to be on the remaining leaves. And in this way, I just chop off leaves until I have 1 left and I have located the robber. So the localization number is 1, but the metric dimension is S-1. So we can have an arbitrarily large difference between these 2 parameters. The next question that we considered was, that this is not due to us, it's a very old result. So one of the questions that you can consider is if we know that it reaches the bottom and we know that it reaches the top, what happens in the middle? And we can make use of this idea of a star and expand it a little bit, no pun intended, to show that for every pair of positive integers n and k, where k is less or equal to n-1, there exists a graph of order n with localization number equal to k. And to find that, it is the complete graph, kk, and you join it with the empty graph of the remaining vertices. And if you look at this graph, you can see that it sort of looks like a star. It is a star where the center vertex is expanded to a complete graph. So I think it's a blow up when you do that to every vertex, but this is just for the center vertex that we do that. And then we can easily show that we need k vertices to find a robber on this graph. And it's very similar to our arguments both for the star and for the complete graph. So if you look at the complete graph, I can never find the robber if I just probe 3 vertices, because if I probe 3 vertices, then, or 4, let's start with 4. If I probe 4 vertices in the center of the graph, in that K5, then the endpoints of this star-like structure would all be in the same vertex, in the same safe set. So then when the robber can move, he can once again move to the whole graph, and we're back at square 1. And the same if we probe less than 4 vertices in this complete graph in the middle, the black part, then I'll have a safe set in that black bar. And then again, the robber can be anywhere in the next step. So we can never have less than k cops if we want, or k probes if we want to locate the robber on this graph. Sorry. Now, thinking about these examples that we just did, and with the complete graph being such a difficult graph in terms of you need a lot of probes to solve it, when I first started thinking about it, it made me think about the coloring problems and the connection to the click number of a graph. Because when we look for a proper coloring, then we know that it must be at least the click number, as one of the speakers did yesterday in his talk, because you need at most the number of vertices in a complete graph to have a proper coloring. And in here, it feels kind of like the same idea. So maybe if I have a large click, then I know how many cops I need. But unfortunately, this is not true, because the parameter of localization is not monotone on taking subgraphs. And we show this by making use of this double house graph. So if we consider this graph, it is a K4 with two little roofs added to it, then we can show that this graph has a localization number of 2. And that is if we probe the vertices outside of our click, our maximum click. And if we do that, then all the vertices of that K4 will have different distance vectors. So the robber would be immediately located in this graph. But if we take that V, vertex V, away, then we can't do that anymore. Then we need at least 3 cops to find a robber on this graph. So when we take a subgraph, it's possible that our parameter can increase. And therefore, we can't say that the localization number of a graph is strictly bigger than the click number. But we can find some results by using the click number. You'll also notice, if you are familiar with results on the metric dimension, that many of these things look pretty much the same. And that is because in these graphs, like the complete graph, you have to find the robber on the first turn, otherwise you will never be able to find him. And then we are closing in on the metric dimension. So this is then the result in terms of the click number, and it shows when I can hide out in a click. So I'm saying the robber is hiding on a click, and that is when he can always stay in this click, and it doesn't matter how many cops, or it doesn't matter where you probe, it will always be able to get away in that click, and we will call it a hideout. And we can show that the localization number will always be bigger or equal to log 2 of the click number. And the reason why this works is if you have your localization number equal to k and you probe k vertices. Now think about the distance from that probed vertex to any vertex in your complete graph. So the vertex will either be a distance I from the vertex in the complete graph, and the moment you're in the complete graph, you're 1 away from everything inside that click. So for a specific probe vertex, every vertex in the click will either be distance I or distance I plus 1 from the probe vertex, which means that there's only 2 possibilities for a distance to the number or to the vertices in the click. And that means there is a total possibility of 2 to the power of k different distance vectors that we can consider. And therefore, the click must be smaller or equal to 2 to the power of k, which then gives us our bound on the localization number. Some other work has been done also on where a robber can hide in a graph. When we talk about a robber that's hiding from a graph, we should always specify the number of cops that you're playing with. So when the localization game was first introduced by Sega, I think in 2014, she introduced it as a game played by a single cop. And then it can't be in 2014 because this paper is from 2012, so it should be earlier. And then Caro and friends showed that when we play with one cop, then the robber can always hide in a small cycle of order less than 6. So whenever you have a cycle of 3, 4, and 5, then we know that the localization number must be at least 2. And I'm just quickly going to explain why this is true if we look at the cycle itself. So when we have just one cop and we probe the vertex, or we have just one probe, we probe a vertex, then in this 4 cycle, 2 things can happen. We can either get a non-adjacent safe pair, like in this first figure, or we can get an adjacent safe pair, like in the second figure. Now, if we look at what the robber can do in the next step, so if it is a non-adjacent pair, when the robber moves, he can move anywhere in the cycle again. So he can be safe in the cycle again. Same thing if we have an adjacent safe pair. The robber can still move anywhere in this 4 cycle. So it doesn't matter where the cop probes, the robber can have a winning strategy just by moving to the appropriate safe pair from where the robber the cop is probing. So from here, this is my kind of general results. I want to move on to specific graph classes. And there's some really nice results. I always think if I talk to my students about tackling a problem in graph theory, so you look at the problem and find some nice, easy general results, and then you try and avoid cycles for the life of you. You just don't want to touch a cycle first. So you have to go to a tree. So my question here is, can a robber hide from a cop in a tree? Now, if you look at these 2 trees, the answer is sometimes. I want you to see whether you can figure out, just like a hunch, which one of these 2 trees can a robber hide in from a cop, one single cop? So for which one of these 2 trees will the localization number be 1? So it's always kind of weird when you don't have an audience in front of you, and when you ask a question, it's just like a blank screen. So in my mind, I imagine it's like my kids when they watch a TV program where the character asks something, then they shout out in front of the TV the answer. So I'm imagining all of you shouting out, it is the right-hand side tree where the robber can hide. So I really hope that's true. And if you just think about what a real robber will do, hiding from a real cop, then he's certainly going to do better if there's more leaves. And that's the only difference between these trees. There's this one single extra leaf in the right-hand side, which makes it easy for a robber to hide. So the condition is not really because there's more leaves. I just thought it was quite funny that it ends up that if it's there's one more leaf, a robber can hide. The real reason why the robber can hide in there is because of the substructure that I showed there in red. And whenever we have the substructure in a tree, the robber can hide from a single cop in there. So this result is due to Sega, and she showed that for any tree, the localization number would be smaller or equal to 2. And specifically, the localization number is 1 if and only if T does not contain that red subgraph, which is this one here, T33, as a subgraph. So we have a very nice characterization for what the localization number of T's looks like. Now, I actually started this. I'll tell you where I've heard about this topic. It was at a CID, I think it was a while ago, or maybe Magda, it was one of the Gdansk graph theory conferences. I heard someone spoke about the localization game, and I couldn't find a student who was interested in the topic until 2 years ago. So I have a master's student that worked on the localization game on Cartesian Products, which is our next special class, and he's defending his master's thesis on Friday. I'm very proud of him. So we are going to quickly look at the Cartesian product of graphs. And just to make sure that we all know what we're talking about, when we say Cartesian product, I'm just going to do it with an example because it's so much easier to visualize it. So we have here P6 of order 6 and a cycle on 5 vertices. So if you look at the Cartesian product of graphs, you will have 5 copies of P6 and 6 copies of C5. So if you look at this red encircled graph, that would be a C5, and every row in this graph is a C5, and we have 6 of them. If you look at the columns, you'll see that that's a P6, and every column is a P6. That would be our Cartesian product of 2 graphs. Now, in general, John Ray showed that there is a very nice lower bound in terms of the localization number of these 2 graphs. If you take the Cartesian product off, you must always have at least the localization number of one of these graphs. And then obviously 2, because we said that on a 4 cycle, you can hide from 1 cop, and a Cartesian product always have 4 cycles, so it must be greater or equal to 2. And the reason why this works, if we can just go back. Why doesn't it want to go back? There we go. If I probe less than the localization number of my graph, then the robber can hide in that copy of, let's say, C5. So it can always hide in here if I probe less vertices than the localization number of that graph. Now, Bosek and friends showed in 2018 that they can also find an upper bound in terms of the maximum degree of these graphs together with the localization number of the specific graphs. And we are going to make use of, or we made use of the doubly resolving number to show that we can, for certain graph classes, improve on their bound. And the idea is, once again, from something very similar to a metric dimension. But firstly, what is a doubly resolving number? So remember, we said that the resolving set uniquely identifies the vertices from their distances. Now, a double resolving set takes it a little bit further, and I'm just going to explain it quickly by looking at an example. So what it says is that if you have a set, then every 2 vertices, not in the set, actually in the set as well, every 2 vertices in the graph, for every 2 vertices, there must exist 2 vertices in your set such that the difference between the distances to those vertices are not the same. So we're going to look at the colors. It's easy to do with the colors. Let's look at the 2 vertices on the left-hand side of the green one. If you look at the blue and the green colors, you will see that their differences are the same. 2 minus 1 is 1 and 3 minus 2 is 2. But if we consider the blue and the orange distances, we can see that it differs. 3 minus 2 is 2, 3 minus 4 is minus 1. So that means that the blue and the orange vertex doubly resolves those 2 vertices. And this is a very important concept if we want to show our upper bound. So this brings us, this is just mentioned that every double resolving set is obviously also a resolving set. So it bounds the metric dimension from above. So we've managed to show that the localization number of 2 graphs will always be smaller or equal to the localization number of the one plus the doubly resolving number of the other one minus 1. And how we do that is we choose a probe as follows. In the graph G, where we have the localization number, you are going to probe your first probe of the known strategy for graph G. And then in the copy of H, you are going to probe a double resolving set. And you're going to make sure that where they overlap, there is a vertex, because we can just probe any copy of H. So we make sure that there's one vertex that overlaps, and that's where the -1 comes from. And then what this does is, because we are probing a double resolving set in H, we know that every single one of these rows, now all the safe sets will be contained in these rows. We won't have safe sets in the columns. And then by making use of the double resolving number, we can show that we won't have a safe set spanning 2 columns as well. So I'm just going to illustrate the idea of this proof by an example. And we're going to make use of C8 and P10. I actually think I've swapped the direction of the proof and the example, but it doesn't really matter. So here we have a C8 and a P10. Now the localization number of C8 is 1. We've done that in the very beginning. And I think you would easily convince yourself that the double resolving set of P10 is 2. It must be at least 2, and we can do it with 2. You can check all these distances. In this grid represents the vertices in our graph, and the top value is the distance from the left cop, and the bottom value is the distance from the right cop. And you can see that the difference in the row, the difference between these two values will all be different. So it is a double resolving set. In the next picture, I highlight for you where our safe sets are, because it's quite a little bit difficult to see. You have to concentrate quite hard. But let's look at the first column, and you can see that the purple blocks form one safe set in every column. The green ones, another safe set in every column, and the red ones, another safe set in every column. And we have a strategy for a cycle. So if we just consider the one column and we look at those two red vertices, that's a safe set. We can see that they distance 3 from one another. Now, if you think carefully, we have done this before. We know where to probe. So in the next step, when the robber can move, he can move anywhere to these gray vertices. And our strategy said, probe at the end of the gray band. So we are going to do exactly that. And then you will see that, as expected, everything in that column has a different distance vector. And also in those two vertices next to it, because we know that every column, 2 columns can't have safe vertices, share safe vertices, and therefore the robber is located in the second probe. Okay. I'm going to conclude with some open questions. No, I'm lying. Oh, there's a slide missing, extra slide. So this is just some results to give you an idea. By using this theorem we just have, and then some other ideas, we've managed to improve on this theorem for complete graphs by a general graph GM of order n, and show that that is small or equal to the maximum of n-1 and m-1. And in some cases, this is an extreme improvement on the bound in terms of the double resolving number. My student also showed that for the product of cycles, you mostly need 2 cops. In some small cases, you need 3. And then one of the interesting things is when we considered stars. So if you think about trees can only be 1, the localization number can only be 1 or 2. But if we look at the product of stars, you had to use nearly half of the leaves in order to get, it is half of the leaves, in order to capture the robber. So now let's look at some open questions. One is in terms of hideouts. So we know that if we're playing with 1 cop, then a small cycle is a hideout. We know how many cops we need if we know the size of the click. But is there other specific structures that we can find? Like for trees, we know what the substructure is. So if we fix K and say, what if we use 2 cops? Can we find a structure that will be a hideout for a robber, so that we need at least 3 cops? So thinking in terms of Cartesian products, as I mentioned, this result of Chandra in terms of the complete graphs was a huge improvement already, but it just shows me that there's still room for improvement, and it will be really great if we can find a better upper bound for general products. I'm really interested in looking into the Cartesian product of trees, just to see if there isn't some interesting pattern in terms of the number of leaves. So my gut is to next try something, and also work with things where the resolving set, the metric dimension, and the localization number differ quite substantially. So I want to look at combs next and see what happens. And then this is just one type of product. So you can consider quite an array of products, for example, the direct product, and see what happens to the localization problem or number in that cases. Then finally, something that I will always find very interesting is to see what happens to a parameter if small changes happen to the graph. And this can be many things, but for today, I'm just going to focus on one, which is edge removal. So if we consider a cycle of 6, I've indicated that the localization number would be 2. And if I take away one edge, then I'm left with a path on 6 vertices. And the localization number of a path is 1. So we see that there's definitely cases where if I take away one edge, then the localization number decreases. But if we once again go and look at that double house graph, and in this case, just take away the edge xv, then we can once again see that the removal of an edge can also increase the localization number. So it'd be really interesting to know which type of edges will cause the localization number to decrease, the removal of that edge, or for which type of edges will the removal increase the localization number. And then move on to criticality and see are there graphs where if we take away any edge, that it will always decrease or always increase? Or is it always that there will be one edge that will never increase or decrease the localization number? That's it from my side. Thank you so much for listening.
Thank you so much, Riana, for your very nice, interesting talk. I just want to make sure that this results for Cartesian product, it means that your student preparing a master degree, he has to solve new problems and find new patterns.
So he did this, yes, for his master's, but it's not required. So okay. It's never required for a master's, but it's certainly much more fun.
Okay, thank you. Thank you. And if anybody has any questions, I think we can ask questions using chat on Facebook and chat on YouTube. Maybe Julian can ask, check if you have any questions.
There is one question on YouTube. Did you consider a subdivision of edges?
We have not, but there's some work done on subdivision of edges where they show that, but this is specifically for when you play just with one. No, I think I'm lying. This is for both games, just with one edge and with more. And they have shown that if you subdivide an edge multiple times, how many times can you subdivide it before the localization number changes? So there is some nice results regarding that.
Yeah, it's nice.
Thank you.
I have another question. Which families of graphs have been studied of the localization parameter, like, well, just trees and but are there any others? Just it is quite recent.
Yeah, so in general, also outer planar graphs. And for outer planar graphs, it's shown that the localization number is always less or equal to 2. And then there's some results on geometric graphs, I think. And now I can't think of something very general. Some things are sorted out, like complete bipartite graphs and things like that. Yeah. I think that's it.
Thank you. We have some comments on YouTube. Very nice talk. Thank you. Nice talk. Thanks.
Pleasure.
The same here on chat. Very nice talk. Very interesting talk.
Okay. Are there any more questions, comments? Some solutions of open problems?
If anyone has ideas on how to find some algorithmic angles, so there's some complexity results, but I have a student that is just for holiday work attempting, I think Jenna is listening, to find an algorithm for doing this. So if you have ideas, send them our way.
Okay.
No more questions.
No more
Okay,
questions.
I'm going to stop sharing my screen.
Okay. So I think I want to thanks to Riana once more time for your interesting talk. And I don't know if other organizers want to say something.
I don't know. I like to say thank you very much, Riana. It was very nice talk and very interesting topic. And
Thanks, Rita.
yeah, I like a lot. Thank you.
Thanks, Rita.
And I hope that nobody had a problem to understand, to follow. It's very nice examples and everything.
Thanks, Maya.
That's very, very clear. Okay, so the boss, Julian.
Thanks a lot for the talk. It was really nice and really interesting. And I was
Thank
looking
you.
if there were another comments, since there is a small delay between the broadcasting, about 20 seconds. So I was checking. But I think that would be all for today. We are in a few minutes. We're uploading the videos from today and the posters, and we will share them on YouTube and on Facebook. Don't forget to subscribe to this channel and to follow us on Facebook.
Okay, thanks a lot.
Okay,
Thanks,
thank you.
Riana.
And we invite Riana, as always, to say goodbye and see you tomorrow in your language, please.
Tot ziens, sien julle môre.
Okay, thank you.
Yeah.
Very nice to see everybody.
Oh, it was.
Okay.
Bye. See you tomorrow.
Bye.
Bye.
Okay, see you tomorrow. Bye-bye.
Bye. Bye.